Hi. In this video, I want to talk about what happens to conjugacy classes when we pass to a normal subgroup. So before I explain what any of that means, let me give the setup to the video, and we'll introduce some notation and stuff like that. So the setup for all this video is going to be that we have an element X inside a subgroup H, which is normal inside a group G. So we have this normal subgroup H, we have an element of H called little x, and we're going to think about the conjugacy class of little x in two different ways. We can think about X, or I really mean two different conjugacy classes. We can think about X as an element of the group H, or we can think about X as an element of the group G. And either way, we get some conjugacy class, and we could wonder, like, what is the relationship between these things? So let's first think about the H conjugacy class. And I'm going to denote that by O sub H of X. And I'm using that notation the O is for orbit. So we're talking about the orbit of X under the action of H on itself by conjugation. H acts on itself by conjugation, and the orbits are precisely conjugacy classes. So what does this orbit look like? It's the conjugacy class of X. That's all the YXY inverse, such that Y is an element of H. And we could compare this to the G conjugacy class of X, which of course would be the exact same thing, but now Y can come from the group G. That's a bigger set, so we have this subset containment between the two sets. So we always have that the H conjugacy class is contained inside the G conjugacy class. And that's the first interesting thing we can note. What this tells us actually is that each G conjugacy class, so if I look at this set O sub G of X, this is going to break into a disjoint union of H conjugacy classes. So the idea is, like, let's say we start with X and we form its H conjugacy class. So its H conjugacy class might be the entire set O sub G of X, but it might be smaller, so this containment might be strict and it might not be. If there are elements that we didn't use up, if there are elements outside of this H conjugacy class that are still inside the G conjugacy class, we can take one of those, let's call it X prime, and then we can look at its H conjugacy class. And the fact we just showed says that O sub H of X prime is going to be a subset of O sub G of X prime. But the whole idea is that this X prime was another thing inside O sub G of X. So X prime is conjugate to X. They have the same conjugacy class. So here we get this equal to O sub G of X. So every time I pick another element that I didn't use up yet and I take its H conjugacy class, that'll also be a subset of O sub G of X. And we can keep doing this until we completely exhaust O sub G of X. And we're going to get this decomposition, this splitting of this conjugacy class O sub G of X into different H conjugacy class pieces. And that's what we want to talk about in this video. The most interesting thing we can say about this right off the bat is that all of these pieces are going to have the same size. So that's for a fixed x, that is. If I just think about one particular value of x, then all of these different O sub h's are going to have the same cardinality inside here. So we're going to split O sub g of x into a bunch of equal-sized pieces. That's what we're going to show next. Okay, so as promised, we're going to show that all the different H conjugacy classes inside a given G conjugacy class have the same size. And the way we're going to compute this is to use the orbit stabilizer formula to write down the cardinality of one of these conjugacy classes. So we're going to have this element X, the setup is the same as before, and we're going to look at the size of its H conjugacy class. By the orbit stabilizer theorem, that's equal to the index inside the group H of the stabilizer of little x under this action. I'm going to do a stabilizer sub h to remind ourselves that this is with respect to the h action, the action of h on itself. Okay, now I'm going to remember, let me do this in a different color, that if I were instead, so we have this bigger group G, and I could also look at the index of the stabilizer of x inside big G. And we can decompose this as a product. This is the tower rule, it's usually called. And as such, we could take this thing here, that's this term right there, and write it as the index of stab hx in G divided by the index of h in G. Okay, so we're going to do that next. Okay, now next we're going to think about the relationship between between stab sub h and stab sub g. So stab sub g is going to refer to the stabilizer of x with respect to the action of g on itself by conjugation. As a side note, these are just called the centralizers. That's what those things are. So if we look at the centralizer in g of x, we're going to, let me do that again in blue. So maybe I could say it this way. So stab sub h of x, this is the set of all y in h such that yx, y inverse equals x. That's what it means for y to be in the stabilizer. Again, that's the same as being in the centralizer of x. And this, of course, is a subset of all the y in G such that yx, y inverse equals x. But we can say a little bit more than that. Let me just refine that claim a little bit. This H stabilizer here is equal to the intersection of H with the set of y in G, such that yx, y inverse equals x. Right, that's pretty clear. And this is H intersect the G stabilizer. So in particular, that's a subgroup of the G stabilizer. And that tells us that we can take this index, the index of stab sub H in G, and write this as a product. So the first term is the index of stab sub G times, next, the index in stab sub G of this intersection, H intersect stab sub G. Okay, so let me write that in next. So we're breaking into this product here. Oh, and I should also notice that this term here, that's the size of the G orbit of x, again by the orbit stabilizer theorem. So what we have here is the size of stab sub gx, the index inside stab sub gx of H intersect stab sub gx over the index of H and G times the size of the G orbit. So that's the formula we have. We have a way to write down the size of the H conjugacy class in terms of the G conjugacy class times this other constant here. And we can notice that this denominator isn't changing, right? That didn't depend on x at all. And so we can wonder, does the numerator change as x varies among things inside the G conjugacy class? And that's exactly what we're going to show doesn't happen. If we can show that this term in the numerator is independent of the choice of x, or rather wouldn't change if we replaced x by one of its conjugates inside G, then what we've shown is that each of the elements of the G conjugacy class will have the same size of its H conjugacy class, and that's exactly what we claimed was going to happen. Okay, so let's take another element, x prime, inside the G conjugacy class of x. That means we're going to have x prime equal yx, y inverse for some y in G. Now, let's try to understand what is stab sub H of, oh, sorry, that's not what I mean. What is stab sub G of x prime? Okay, so this is going to be all the z in G, such that z x prime z inverse is equal to x prime. And we have this other way to represent x prime, so let's rewrite this as the set of all z in G, such that z y x y inverse z inverse equals y x y inverse. So that was just us replacing x prime with our expression for x prime. And then I can rewrite this again by taking that equation and multiplying, or like deconjugating by y. So we get y inverse z y x y inverse z inverse y. Yeah, that this equals x. And that's the same as all the z in G, such that y inverse zy is in stab sub G of x. That's just noting here that this element and this element are inverses. You can just check that. Okay, so that's another conjugate here. And okay, so what we have is that we can rewrite this. Oops. So what would it mean for something to be in this set now? It means that if I conjugate by y inverse, I end up in stab sub g. Maybe I can rewrite that as saying the set of all z in g such that z is in y stab sub g of x, y inverse. And of course, that's just the set, y stab sub g of x, y inverse. So we know what happens when we take this x prime when we look at its stabilizer. It's just a conjugated version of the stabilizer of x. Okay, so here's just a reminder of the equations we have so far. We have this expression for the size of the H conjugacy class of x in terms of the G conjugacy class of x, this constant, the index of H, and finally this last term that we're especially concerned about. We want to know what happens as x changes. And we chose this other conjugate x prime, and we want to understand what's the size of its H conjugacy class. And we're going to do that by understanding that index over there. So the thing to notice is that conjugation is an automorphism of a group. If I conjugating by y in this case is an automorphism of G. And that means, well, we'll have this group y stab sub gx y inverse. This will still contain the conjugated version of y h intersect stab sub g x y inverse. That's easy. And so we'll have this a subgroup of this, and then the index here is going to be the same as what it was before. That's because the map was an automorphism, preserves indices. That's a good exercise if you haven't seen it. So this would be the same as what we started with. That's this stab sub gx h intersect stab sub gx. Okay, so I'm saying that when you conjugate your subgroups of a group, the indices don't change, preserves indices. Okay, so now, well, we understand this first group I wrote down. That was stab sub g of x prime, right? And this next group, well, you can just check that when I conjugate an intersection like this, it's the same as conjugating and then intersecting. And then that second term is again stab sub g of x prime. But also remember that h was normal, and so y inverse is just the same as h. So the whole point was that was the same as h intersect stab sub g of x prime. Okay, and that pretty much does it. What we have here is the same term that we started with, but now with an x prime instead. So what we're saying is that if I start with this element x, and then I take some other element x prime that's conjugate to x inside g, this term in the numerator of O sub h of x hasn't changed, and as a result, the size of the H conjugacy class of x and the size of the H conjugacy class of x prime are going to be the same. Okay, so now we know that whenever we have an element x inside G, an element x inside H, and we take the size of its H conjugacy class, we're always getting this quantity, which is the index of the centralizer of the G centralizer of x, inside the G centralizer of x, the index of the H centralizer of x. And then we're dividing that by the index of H and G, and that's times the size of the G conjugacy class of x. Now, we already knew, I think we argued earlier, that O sub h of x is a subset of O sub g of x, so the cardinality of O sub h of x has to be at least less than or equal to the cardinality of O sub g of x, and that means that this fraction here has to be less than or equal to 1. But we can actually say something a little bit more, which is that we also just proved that O sub g of x splits into pieces that all have this exact same size. It splits into an integer number of pieces, all of this size, and that means the number of pieces is exactly 1 over this fraction here. So the number of H conjugacy classes in O sub g of x is the reciprocal of that fraction, the index of H, divided by the index of the H centralizer of G in the G centralizer, the H centralizer of x in the G centralizer of x. And this has to be an integer, a positive integer, I guess. So what can we say about this? It says that the index of this stabilizer divides the index of H. So that's kind of interesting. In particular, we could think about the case where the index of H is prime. So if this number is prime, then this number has to either be 1 or the index of H. And that means this quantity is either going to be 1 over that prime or 1. Or in other words, the number of pieces that, if the index of H is prime, then the number of pieces that O sub g of x splits up into is either 1 or that prime. So that's not very important, but it is interesting at least. If the index is a large prime, that tells you really quite a lot. In any case, we're going to look at an example of some splitting of conjugacy classes next. The example we're going to use is the alternating group A5, which sits as an index 2 normal subgroup inside the symmetric group S5. Okay, so we're going to look at the example where our normal subgroup is A5. We could use AN, but I'm just going to keep it particular with A5, so we have specific things to work with. And this is a normal subgroup of S5. It's a subgroup of index 2. Okay, so we better understand the conjugacy classes in S5 first, and we can recall that these are given by cycle types. So I'll explain that briefly. Remember that every element in S5 can be written as a product of what are called disjoint cycles. So let me give an example. We could take an element like 1, 2, 3, 4, 5. This is a simple example. And this first term, this is a cycle. This refers to the element of S5 that sends 1 to 2, and sends 2 to 3, and sends 3 back to 1, and keeps everything else fixed. And the 4, 5 sends 4 to 5, and 5 to 4, and keeps everything else fixed. And together, their product, well, these two elements of S5 actually commute, it turns out, just because they modify disjoint sets of elements. That's what we mean by disjoint cycles. They keep everything fixed besides these few elements that they're moving, and the elements that they're moving don't intersect. So these two elements of S5 commute with each other, and their product is the element of S5 that sends 1 to 2, and 2 to 3, and 3 to 1, and 4 to 5, and 5 to 4. That's that element. But every element of S5 can be decomposed in this way. It's a good exercise to work out why that's the case. Anyway, the thing to remember is that when we conjugate a product of cycles like this, well, first of all, conjugation is a homomorphism, so it splits up like this. And then we can remember when you conjugate a cycle, you just apply the element of S5 to the symbols inside the cycle. That was a little vague, but hopefully you can see by what I'm writing what happens. And so if I take a product of cycles like this, and I apply, if I conjugate by sigma, I end up with still a cycle of length 3 and a cycle of length 2. And this list of lengths is what we call the cycle type. So this element 1, 2, 3 times 4, 5, that has cycle type 3, 2. And this element sigma 1, sigma 2, sigma 3 times sigma 4, sigma 5, that has also cycle type 3, 2. And I should make a quick note about our conventions for cycle types. First of all, the cycle type is really unordered. I'm writing them as like ordered tuples here, but in general we should think of them as being unordered. I would count 3, 2 as being the same cycle type as 2, 3. And also when I write my elements as products of disjoint disjoint cycles in order to find their cycle type, I want to make sure I use all the symbols 1, 2, 3, 4, and 5 when I write down those cycles. So for example, the identity element of S5 is the empty product of cycles, but it's also the product 1, 2, 3, 4, 5, like this. Here, each of these cycles is the identity, but I'm writing it this way so that I have it as a product of disjoint cycles where all the numbers 1 through 5 have been used. So this element, the identity, I would say has cycle type 1, 1, 1, 1, 1. So we can observe that really cycle types are just unordered lists of positive integers that add to 5. That's all they are. And the conjugacy classes are just cycle types. So we have a complete list of all the different conjugacy classes of S5, and we're going to use that next to find their orders and then study the splitting behavior. Okay, so conjugacy classes in S5 are given by cycle types, and cycle types are just unordered lists of positive integers that add up to 5. So let's write out all the different possible cycle types. The simplest one is just 1, 1, 1, 1, 1. That's the cycle type of only the identity. So how many things are in this conjugacy class? Just 1. All right. Next, we could have 1, 1, 1, 2. That's some numbers that add to 5. And how many things are in this conjugacy class? So the elements of this conjugacy class look like A times B times C times DE. And these A, B, C, D, E could be any permutation of the numbers 1 through 5, but we remember that these things commute with each other, so the order in which the A, B, and C appear doesn't matter. If we move these terms around, we get the same element of S5. So how many ways are there to produce an element like this? Well, I need to pick which two things to have paired up, and that completely determines the element. So there'll be 5 choose 2 things in this class. And so that'll be 5 choose 2, which is 10, is the size of this conjugacy class. All right, next we have another cycle type. That would be 1, 1, 3. So those will look like A, B, C, D, E. And now again, we have to choose which 3 things to group together into the cycle, but we also have to choose which way to have the cycle go. So once I choose 3 elements to go into the 3 cycle, let's say I want to have the cycle contain 1, 2, and 3. Then I have to choose, do I send 1 to 2, and then 2 to 3, and then 3 to 1? Or do I send 1 to 3, and then 3 to 2, and then 2 to 1? Basically, there are 2 ways to go around a triangle. So we have to choose one of those 2 ways after we pick which 3 elements to stick together. So the answer here should be 2 times 5 choose 3. 5 choose 3 is also 10, so this is 20. Okay, now the next thing we could have is 1, 4. And here it's the same kind of story. We pick which 4 elements to have together, and in order to traverse around those 4 elements, there are 2 ways to go around a square. So this will be 2 times 5 choose 4, and that is just, 5 choose 4 is 5, so that should be 10. Okay, and then we could have just a 5 cycle, and so how many ways are there to do that? We have to just line up. Oh wait, sorry, I made a mistake here. So the 2 times 5 choose 3 is correct. We just pick 3 elements and then a way to traverse around them. But when we pick 4 elements and then a way to traverse around those, there aren't just 2 ways to do that. So in the 3 element case, I have A, B, C, and I have to go either from A to B or from A to C, but once I choose to go to one of those, if I go to A to B, then B can't go back to A, or else this wouldn't be a 3 cycle, so that determines the rest of the whole thing. Okay, and if I went to C instead, then C would have to go to B because it can't go back to A, and B would have to go to A, so that determines the whole thing. However, when I have 4 elements, I have more choices than that. So when I take 4 elements, here's one way to think about it. I write out my 4 elements that I've chosen, and I can permute them however I want. So there's 4 factorial ways to permute those 4 elements. But then I realize that some of those permutations are the same. So A, B, C, D and B, C, D, A are actually the same. You can just check. The second one also sends B to C and C to D and D to A and A to B. That's the same bijection that we were talking about. So these 2 cycles are equal, and each cycle, it turns out, can be written down in exactly 4 ways by rotating it around in these between 1 and 4 times. Okay, so the 4 factorial lets us put the elements in any order, but we have to divide by 4 to cancel out the overcounting that we did of all the cycles, and that gives us 3 factorial ways to do this. So so this 2 before was really a 2 factorial, and next, instead of a 2, we're going to have a 3 factorial. Okay, so that was my mistake. 3 factorial is 6, 5 choose 4 is 5, and 6 times 5 is 30. So let's get that in there. All right, so hopefully that's corrected now. And for 5 cycles, it's kind of a similar story. I have to choose all the elements, and then I can order them however I want. There's 5 factorial ways to do that, but each 5 cycle can be written down in 5 distinct ways via rotation. So what we end up getting is 5 factorial over 5, which is 4 factorial. So that's 24 different 5 cycles. All right. And now we can think about the remaining cycle types. So let's see, what else could we have? We could have a 2 and a 3. Notice that I exhausted all the possibilities already. I exhausted all the possibilities where there's at most one number that isn't 1 in the cycle type. So all the remaining cycle types are going to have at least 2 numbers that aren't 1. So 2, 3 is one of those. And how many ways are there to do that? Well, we pick, let's say, which 2 things we want on their own. Or let's say we pick which 3 things we want. To be in the 3 cycle, and then we determine the ordering on the 3 cycle, and the other 2 things have to be paired up. So it's actually the same as 113. Every element of cycle type 113 corresponds to an element of cycle type 23 by taking the 2 elements in their cycles of size 1 and merging them together into a cycle of size 2. So again, that'll be 2 times 5 choose 3, and that's 20. Okay, and then what else could we have? Let's think. So I could have a 1, 2, 2. That would be a way to do it. And the 1, 2, 2, how many ways are there to do this? Well, I need to pick 2 elements from 5, and then 2 elements from the remaining 3, and those will give me my 2 groups of 2, but then I could have picked those groups of 2 in either order. It wouldn't have mattered. So like if I did 1, 2, and then I picked 3, 4, that would be the same as having picked 3, 4, and then picking 1, 2. Those give you the same product inside S5. So I will have double counted everything in that way, so we should divide by 2. So I think in this case, it should be 5 choose 2 times 3 choose 2, all divided by 2, and that's 10 times 3 divided by 2, which should be 15. All right, and what's left? Well, if there's at least a 1, 1, then we have to add up to at most 4 with the remaining numbers, and they at least 2 of them have to be bigger than 1, so it would have to be 2, 2. So this 1, 2, 2 is the only remaining one, I think. Yeah, we can tell that we're done, because if we add together the sizes of the conjugacy classes that we've produced so far, we do get 120, which is the order of S5. So we must be done. So now let's try to understand how these conjugacy classes split when we move to A5. Well, first of all, some of these classes don't even appear inside A5, right? There are elements of A5 that aren't of these cycle types, and we can tell because the sign of a cycle is the opposite parity of the number of things in the cycle, if that makes sense. So like a 2 cycle, a transposition, is an odd permutation, whereas a 3 cycle, something like 1, 2, 3, that's an even permutation, etc. And so now we can think about for each of these cycle types, is it in A5 or not? So first of all, this cycle type 1, 1, 1, 1, 1, that is in A5 obviously because it corresponds to the identity. But why is that? So a cycle of length 1 is even, and this is a product of 5 even cycles, so that's still even. All right. Then we could look at 1, 1, 1, 2. Well, that's 3 even cycles times an odd cycle. That's going to be odd. So that one is not going to be in A5. And then we can think about 1, 1, 3. Well, that's an even times an even times an even. That will be there. I don't know what I was using, what color that was before. Maybe like this? Yeah, that was it. Okay. So I'll try to stick with that. So that one will be inside A5. And then 1, 4, that's an even times an odd. That won't be in there. 5 is an even. That will be in there. 2, 3, that's an odd times an even. That will not be there. And 1, 2, 2, that's an even times an odd times an odd. We will have that one. Okay, so these remaining conjugacy classes, the conjugacy class of the identity, the one of cycle type 113, and the one of cycle type 122, those are going to be, the cycles of length 5, those are going to be the conjugacy classes that remain inside A5. So we have these conjugacy classes that actually exist inside A5. The other ones don't exist at all, and these have to split into a bunch of pieces. All right, so we're going to try to understand the splitting of these, and we can just look at their orders to start. we remember that the splitting, or the size of the, or sorry, the number of pieces into which this split was the index of the subgroup, so that's going to be 2 in this case, A5 has index 2, divided by, for each, if we take X an element of one of these conjugacy classes, the index in the G centralizer of X of the H centralizer of X, which was the intersection with H. In this case, G is S5. I'm going to leave it as a G here just because I already wrote G and I am lazy. But this I'll make an A5. Okay. So this is the number we're going to get, and of course this number has to be either 1 or 2. That's the only way for this to be an integer. So the number of pieces that these split into, these either stay whole or they split into 2 even-sized pieces, and immediately we get the answer for 2 of these. If the conjugacy class has odd size, it can't split into 2 even-sized pieces. So these stay together. This one stays together, just because the sizes are odd. And then we have to actually wonder about these two. Do these two classes split or not? They might split into 2 pieces and they might stay together. All right, so how are we going to understand that? Well, the classes are going to split into 2 pieces if and only if this number is 2, which is if and only if this denominator is 1. So we have to understand, for these 2 conjugacy classes, does this denominator equal 1? And of course, if the index of the A5 stabilizer is inside the S5 stabilizer equals 1, then those 2 subgroups are going to be equal. So what we have is that the conjugacy class splits if and only if the A5 stabilizer of X equals the S5 stabilizer of X. Or in other words, remember the A5 stabilizer of X is just the intersection of the S5 stabilizer of X with A5, and so the only way for those 2 things to be equal is that the S5 stabilizer of X, that's if and only if, this is a subgroup of A5. So the conjugacy class is going to split if and only if everything in the centralizer of X is an even permutation. So we're going to write that out on the next slide. Okay, so these were the 2 conjugacy classes we were concerned about. These might or might not split, and they have sizes 20 and 24 respectively, and we showed that these are going to split if and only if, when we take an element of the conjugacy class, the stabilizer of that element under conjugation, so in other words, its centralizer inside S5, is a subgroup of A5, is entirely contained inside A5. So that's just what we're going to figure out in both of these cases. Let's start with the slightly simpler one, and that's the case of a 5-cycle. Okay, so we want to take a 5-cycle and understand its stabilizer. In particular, we want to figure out if the elements of the stabilizer are going to be inside A5. Well, one thing is that the orbit stabilizer theorem tells us that the size of this orbit, which is 24, is going to be the index of the stabilizer. So the stabilizer has index 24 inside a group of order 120, and that means the order of the stabilizer is 5, which implies, so if I take a 5-cycle in particular, then the order of the stabilizer is going to be 5, and that means that the stabilizer is generated by an element of order 5. What's it going to be? Well, if we take a 5-cycle, I can tell you what the element of order 5 in its stabilizer is going to be. It's itself. That's an element of order 5, and it stabilizes itself. If I conjugate this element by itself, I get back the same element because the element commutes with itself. So we know that the stabilizer of any 5-cycle is the subgroup generated by that 5-cycle, and every 5-cycle is inside A5. Therefore, the stabilizer of any of these elements is contained inside A5, and we conclude that this conjugacy class does split. So that one does split. Let me use a less thick marker. So that one splits. Just because directly, just by counting, we saw that the only way to stabilize this is by powers of itself. Okay. Next, what about the things of cycle type 113? So we can try to pull the same trick. We can think about the index of the stabilizer. Well, the index of the stabilizer would have to be 20. We're inside a group of order 120, so the stabilizer has to have order 6. So let's see if we can identify what the elements of the stabilizer are going to be, and let's look at some particularly nice cycle of type 113. So let's say 1, 2, 3, 4, 5. if we can find 6 distinct elements that stabilize this, we'll know the entire stabilizer. And so then I think the search becomes kind of clear. The 6 elements are going to be like ways to permute 1 and 2, combined with ways to rotate 3, 4, 5 around. But we can actually, from that, just notice immediately that if we flip 1 and 2, that'll keep this the same. So if I conjugate this by the permutation 1, 2, 1, 2 inverse like that, it'll switch the 1 and the 2, so this quantity will stay the same after we conjugate. And so 1, 2, that transposition is inside the stabilizer, and thus the stabilizer is not contained inside A5, because transpositions are not elements of A5. So this one here does not split. All right, and that gives us a complete list, at least of the sizes of the conjugacy classes in A5. We could list those all out, and maybe for the one that splits, we didn't really explain how to find the 2 halves that it splits into. So I'll leave that as an exercise to you. It's kind of good to work out. But it is helpful to know all the sizes of conjugacy classes of elements of A5. For example, you can use this to show that A5 is simple, and it has a lot of applications in representation theory. Okay, so let's just finish up with a conclusion of the list of the sizes of the conjugacy classes in A5. So the numbers we had were 1, 15, 20, and 24 in S5, and then this class of size 24 split into 2 classes of size 12. And so in A5, the sizes of the conjugacy classes are these 5 integers.